system is a group of parts working together to produce a spark that will ignite the fuel-air mixture in the combustion chamber. This spark must occur at precisely the right time in order to achieve the maximum efficiency from the combustion. CDI system's operation is easier to understand if we divide it into smaller subsystems. First, the AC generator circuit. Second, the ignition triggering circuit. Third, the CDI module. Fourth, the high tension circuit. And finally, the ignition controlling circuits, such as the engine stop switches, throttle safety switches, and RPM limiting circuits. All of these subsystems must be working properly for the spark to occur. Let's look at each one individually to identify components and understand how they work. An AC generator, also known as a magneto assembly, is located on the engine crankshaft on all Polaris products. This generator produces the initial voltage by rotating flywheel magnets past the exciter coil. Depending on RPM, the voltage produced from an exciter coil may range from 20 to 100 volts AC. This output is directly connected to the CDI module. Within the CDI module, a rectifier transforms the AC exciter voltage into DC and stores the DC energy in a capacitor. This capacitor has the ability to store and quickly discharge electrical energy. The voltage stored in the capacitor is discharged through the ignition coil primary winding when the silicon-controlled rectifier receives a trigger signal. This silicon-controlled rectifier, or SCR, is simply a high-speed switch, which closes when it receives a trigger pulse. Each ignition coil consists of two separate coils joined together in a plastic housing. The primary side receives the capacitor's voltage, while the secondary side steps it up to a very high level, usually in the range of 20 to 50,000 volts. This high voltage pulse travels down the high tension lead and jumps the air cap at the spark plug, creating the ignition spark. The trigger signal is produced by the AC generator and processed by the CDI module to determine the ignition timing advance curve. There are two ways of generating the trigger signal on a Polaris CDI ignition system. Polaris 3-cylinder snowmobile and personal watercraft engines use a separate external coil to provide the trigger signal. The 400 and 425 cc ATV engines with the 200-watt alternator also use the external trigger coil. As the flywheel rotates, this steel tab passes by the trigger coil, generating a small AC voltage pulse, which is sent to the CDI module to trigger the SCR. The second type of trigger system uses part of the exciter voltage pulse. The positive half of the exciter coil sine wave is used to charge the capacitor, while the electrical components in the CDI module separate the negative half of the exciter sine wave to be used as a trigger pulse. There is no separate trigger coil. In both types of triggering, the signal pulses are processed by various components within the CDI box to determine RPM. The RPM of the engine then dictates whether to advance or retard when the energy in the capacitor is released. This is called an ignition timing advance curve. The entire ignition timing curve can be shifted up or down by manually adjusting the stator plate. We'll look at checking ignition timing in more detail a little later in this program. To identify the type of trigger system used, refer to the schematic diagram in the Master Repair Manual. Some diagrams may refer to the trigger coil as a pulse or control coil. The name may be different, but their function is the same. A 3-wire exciter coil is used on this RXL to provide the voltage that charges the capacitor. The trigger coil is the external type. The 3-wire exciter coil on this 440 fan engine is also used to provide excitation voltage as well as a trigger signal. In both cases, the exciter coils are actually two coils functioning together as one. The first coil produces most of its output at low RPM, while the second coil is more efficient at high RPM. This delivers good AC voltage output over a wide range of RPM. Now that we have a better understanding of how the ignition system functions, let's look at the ignition controlling circuits, the first of which is the engine stop switch. The stop switch may look a little different depending on the product, but the basic function is the same. The stop switches are all located within the operator's reach. In the off position, exciter voltage is shorted to ground, preventing the capacitor from charging, and ignition is stopped. On Polaris personal watercraft, the kill circuit is of the latch type. Once the stop button is pushed, even momentarily, the latch connects exciter voltage to ground until the engine stops turning. The electronic throttle control, or ETC, found on our ATVs, is a simple and effective way of limiting RPM in the event of a throttle mechanism malfunction. A speed limiter module, attached to the bulkhead, monitors engine RPM through a yellow or yellow-red wire from the AC generator's charge coil. When the ETC switch provides voltage to the speed limiter through the white wire, the module shorts the black CDI wire to ground, limiting RPM. When RPM falls below a predetermined ETC limit, the speed limiter module no longer limits RPM. On ATVs produced prior to 1994, a spring-loaded throttle flipper pulls against this lever attached to the throttle cable. When the throttle flipper is released, the lever returns to idle and depresses the ETC switch mounted in the throttle block assembly, even if the throttle mechanism malfunctions. A depressed switch will provide battery voltage to the white wire leading to the speed limiter module. On 1994 and newer ATVs, the ETC switch is attached to a spring-loaded lever. The only time the ETC switch provides power to the speed limiter is when the throttle valve is held in the open position and the driver lets off the throttle flipper. During normal operation, the ETC switch button should be depressed all the time by the throttle cable tension. When the switch is open, internal contacts are closed and battery voltage is provided to the white wire going to the speed limiter module. A speed control assurance is in place on Polaris snowmobiles to stop the engine in the event of a malfunction in the throttle mechanism. The two safety switches, located on the throttle block, are all wired in series. One side is connected to the CDI black wire, and the other side is connected to the engine ground. When the throttle flipper is released, cable tension holds the throttle flipper against switch plunger A. The circuit is open, and the engine is allowed to run. When throttle is applied, pressure is applied to the lever pivot pin, which depresses switch plunger B. The circuit is still open, even though the contacts of switch A have closed. In the event of a malfunction, cable tension is lost, causing both switch plungers to remain outward, completing the circuit and grounding the black CDI wire, preventing ignition spark. Sometimes, diagnosing spark-related problems may seem overwhelming. However, following a step-by-step diagnostic process will quickly lead you to the cause of the problem. First, verify the problem. Check to see if the ignition system is producing good spark. Always verify spark with a new, properly gapped spark plug. The plug may look good and still be partially fouled. Caution: when checking for spark, never lay the plug near an open spark plug hole. The spark may ignite fumes or raw fuel escaping from the open combustion chamber. You can also check spark with an improved spark tester. A 2-cylinder engine should be able to jump a 1/4 inch air gap. 3-cylinder engines should jump a 1/8 inch gap. The next step is to eliminate the control switches. Disconnect the black wire coming from the CDI box, or on snowmobiles, you can disconnect the CDI wire at the kill switches. A partially shorted kill switch may cause an intermittent spark problem at operating engine speeds. Caution: under no circumstances should the machine leave the dealership with the control switches disconnected. It should only be done as a quick test. Inspect the wires and connections within the ignition system. Look for open connections, corroded connectors, or damaged wires. All connector pins must fit together tightly. They should be free of moisture and coated with Polaris dielectric grease. Check to make sure that harnesses and components are all securely fastened. Remove the spark plug caps and check for corrosion. Remove 1/4 to 1/2 inch from the end of the high tension lead and make sure the cap is securely fastened to the high tension lead. A light film of dielectric grease will ease installation and help seal the cap. A loose, corroded, or wet plug cap may cause intermittent ignition problems as well as a weak or no spark condition. If the control switches, connectors, and related wiring are okay, check the resistance of the stator coils using a digital multimeter and compare to the specifications listed in the appropriate repair manual. The color codes and resistance values of the stator coils vary between models. Be sure you check the specifications for the exact model you are working on. Reading should be within 10% of spec at room temperature. If the coil is out of spec, don't forget to check the wires between your test point and the actual coil before you replace a suspect component. If the AC generator coils are within specs, check the ignition coils. On a multi-cylinder engine, each coil should be tested individually. The resistance of the secondary winding should be checked with the spark plug cap removed. Then, test the plug caps separately. A CDI module cannot be tested accurately with an ohm meter, but you can test the voltage coming from the exciter coil and the voltage leaving the module to the ignition coil primary winding. Voltage will vary with cranking speed, so don't look for a specific voltage figure, only that you have at least 20 volts AC or more. You can compare this reading to a similar unit that is working properly. The easiest way to test a CDI module is to eliminate all other ignition system components first and then replace the CDI module with a known good one. On Polaris ATVs, an intermittent spark or occasional engine backfire can be caused by an ETC switch that is out of adjustment or contaminated with moisture. The adjustment of the ETC switch is controlled by the throttle lever free play. The procedure is the same for both ETC switch types. Adjust idle speed to specifications with the carburetor idle screw. Loosen the lock nut on the throttle cable and the throttle block. Turn the throttle cable adjuster bolt until the ETC switch plunger is pushed in completely, and the throttle lever has at least 1/16 of an inch free play. Throttle cable adjustments affect the oil pump on two-stroke engines. Be sure to check oil pump adjustment after setting the ETC switch. Once everything is properly adjusted, start the engine and turn the handlebars full right and full left to see if the RPM increases. If it does, recheck ETC switch adjustment and routing of the throttle cable and wire harness to find the cause of the problem. Backfiring on units with the ETC switch mounted in the throttle block may be caused by a faulty ETC switch, high idle speed, or rich idle fuel air mixture. The idle speed and fuel mixture are very important for proper operation for models built prior to 1994. The snowmobile throttle cables should be adjusted so that there's 10 to 30 thousandths of an inch clearance between the throttle lever and the throttle housing. Easy throttle models should have at least 50 to 60 thousandths of an inch clearance. If this clearance is excessive, the throttle flipper switch contacts will close the circuit before the pivot pin switch opens, causing a bog or a backfire. If adjustments are made to the throttle cable, don't forget to check the oil pump adjustment. Once you have corrected the ignition problem, you should verify the ignition system is operating properly. The correct ignition timing is critical to achieve maximum engine performance. The following procedure can be used to check the ignition timing of an engine. You should always check timing with the engine at room temperature. First, find the timing spec for the model you are working on in the appropriate repair manual. Our 1995 RXL should be timed at 25 degrees before top dead center. According to the chart, the piston should be at 0.139 inches before the piston reaches top dead center. Install your dial indicator in the magneto cylinder. Rotate the crankshaft until the needle reaches top dead center and zero the indicator. Turn the crankshaft the opposite way it turns during operation until the indicator reads the specified measurement. In our case, it's 0.139 inches. This is the position of the piston and crankshaft when the spark should jump across the air gap with the engine turning at 3,000 RPM. Hold the crankshaft in this position and observe the marks in the flywheel through the crankcase timing hole. Take a black marker and draw a circle around the circumference of the hole on the flywheel. Remove the dial indicator and replace the spark plugs and wires. Hook your inductive timing light, Polaris part number 2870630, to the magneto spark plug wire. Start the engine and slowly increase RPM to 3,000 while pointing the light at the crankcase timing inspection hole. To get an accurate reading, you must keep your line of sight the same as when you made your mark. Looking from a different angle changes your viewpoint of the mark, and your reading could be off several degrees. Use the gun sight method to line up 2 points for best accuracy. Observe where the black circle is in relation to the hole opening. If your mark does not line up, stop the engine and reinstall the dial indicator in the mag cylinder. Find top dead center and rotate the crank, counting the distance the dial moves until the mark is in the exact position you observed with the strobe light. Compare this number to the chart in the master repair manual. For example, let's say we find our engine is firing at 0.185 inches before top dead center at 3,000 RPM. If we find EC65 across the top and follow the column down until we get close to 0.185 inches, then follow this line to the left, we find the timing for this 1995 RXL is at 29 degrees. This is showing that our timing is 4 degrees too far advanced. Since our spec is plus or minus 1.5 degrees, we need to retard the timing at least 2.5 degrees. To do this, we need to remove the recoil and flywheel to expose the stator plate. Some engines have marks in the crankcase and stator plate as a reference. If not, use a sharp chisel to make your own reference point. Loosen the bolts holding the stator plate to the crankcase and turn the stator the same way the crank turns to retard the timing, and the opposite way the crank turns to advance the timing. In our case, we'll turn it clockwise about 1/4 of an inch. Generally, 1/8 of an inch is about 2 degrees. Replace the flywheel and torque the flywheel nut to the proper specification. Replace the recoil and recheck the ignition timing.